Do problems from here on out, and I'm gonna just give you my process of thinking of how I come to or draw the conclusion to why I use those equations or how I get the answer. All right, so we're gonna start with plane and composite walls, and so I'm gonna do 3.3a, and so basically it says it's gonna I'll read it. The rear window of an automobile is defogged by passing warm air over its inner surface. If the warm air is at a temperature of 40 degrees C and the corresponding convection coefficient is 30 watts meter squared per Kelvin, what are the inner and outer surface temperatures? So the first step is to draw out the problem and list the given variables. And so as I did here, I did that. And so my next step is I'm going to draw a thermal circuit. And so the way I made my thermal circuit is I decide the processes that happen. So basically, you know, there's going to be convection, then there's going to be conduction through the material, then there's going to be convection from the surface to the air again. So there's going to be three processes. I wrote those out, and then I just added the correlating temperatures. All right, and so the first step I'm going to do is find the heat flux or the heat transfer rate. And so the formulas that I plan on using are, I'll show them to you. I probably should honestly have this already ready, but you know, I try to come as prepared or at least prepared as possible so you guys can see my thinking. All right. Nope. All right, so I'm going to use 311 and 312. All right. So basically I'm going to use, and I'm going to put it in terms of the heat flux. So I'm going to divide out the area, and that's basically to get rid of the areas in here so I don't have to worry about them. So which is equal to the heat flux, which is equal to T infinity outer minus T, oops, sorry, that's inner, because that's the hotter air. Boop. Inner minus T infinity outer, all right, over the resistance total, which is just going to be your thermal circuit, all right, without the area, of course. So, all right, let's put that in terms of, let's put numbers in, all right, so we're going to get 40 minus 10 over, so let's do 1 over the outer, which is 65, or is it 30? One or the other. And then I converted it, they gave you 4 millimeters, I converted it to standard units of meters, so 0.04 for the length of it, over, oh yeah, the thermal conductivity I looked up beforehand, it's in Appendix A3 under glass at 300 K Kelvin, and it's 1.4, alright, so 1.4, alright, plus 1 over 30, alright, which equals, and guys, I'm getting really bad about this, but I don't have much time to write all this out. Try and keep your units, like I've already pre-wrote all this, so I've already done all the math, so just try and write out your units too to see if they cross out. That's a big thing. Alright, so that one comes out to 968 watts per meter squared. Alright, so that comes out, that dearly helps you. Alright, so my next step is I need to find the surface temperature. So I need to find an equation that will correlate the temperature of the surface and the temperature of the air together. And so from that, I'm going to use Newton's law of cooling for the heat flux. Alright, which is equal to, and I'm going to show you guys something so that way it'll make sense to you of why you can do it this way. Alright, so it's up here. I'm going to zoom in a little bit. So here's the heat flux, Newton's law of cooling for the heat flux. Alright, so that's 1.3a. So when it says, when equation 1.3a is used, the convection heat flux is presumed to be positive if the heat is transferred from the surface, and negative if the heat is transferred to the surface. However, nothing precludes us from expressing Newton's law of cooling as the convection coefficient times infinity, air temperature minus the surface temperature. So you can write those two different ways. I just try to keep it as positive. Alright, so let's go back over here. Let's zoom back out. Come on. I got a time limit, which is why it kind of sounds like I'm rushing through this. So we'll keep it as this is the standard method. So basically, I always like to have the Hotted temperature as the positive term in this equation. All right, so let's find T inner, and that means that the air temperature is going to be greater than the surface temperature, so that will be the positive term. All right, so we're going to get Q of H, the heat flux divided by the convection coefficient of the inner, which is, then you get T infinity minus T surface, correct? T surface inner. All right, so we're going to rearrange this. We're going to swap the surface temperature and the heat flux. So T surface I equals T infinity inner. You know what? I need to put inner up there. Be good about it, Cole. All right, minus Q heat flux over the convection coefficient. All right, now let's put some numbers in there. So T of S inner equals 40 minus 968 divided by, let me see, 219. All right. So inner is 30. So degrees C, and I really need to be good about this. I'm sorry, guys. So watts per wasting time. Degrees C, erase that. Sure, we'll do, this is watts squared per meter. Whoops, watts squared. All right, well, per meter squared, and this has units of watts per meter squared Kelvin. So as you can see, those cancel out, and it leaves you with the Kelvin. So that is going to get you 7.7 degrees C. All right. Let me go back to my rainbow color so you can see better. All right, and so now we're going to switch the signs for the other one. So the other heat flux, or the inner temperature. Sorry, the outer temperature. So equals H out, and so the T surface is going to be positive term because it's going to be, here, I'll write it out in a second, because the surface temperature of the outer is going to be greater because it's going to be warmer. All right, so then we're going to divide by Q again, and then H out, and then we're going to add the T infinity, which equals T surface. All right, so we're going to get Q, oops, let me write out numbers now, 968 watts per meter squared over, what is theirs, what's the out, 65 watts per meter squared Kelvin. All right, minus 10 degrees C, which equals the T surface out, which is equal to 4.9 degrees C. And so those are your two temperatures, your two surface temperatures. Inner equals TC, SI, Spanish, 7.7 degrees C. All right, and your T surface outer is going to equal 4.9 degrees C. All right, guys, I will continue chapter 3 problems in the next video. I hope this helped you. All right. Done. Perfect. Let me make sure I did my math all right. Minus, sorry, let's do 968 divided by 30. So 40 minus 32.3, which is 7.7. Sorry.